So right, with the bubble sort, I'll just leave it here. Just ignore this animation for now. With the bubble sort, if I do it n times, even if nothing's getting flipped, I guarantee it's working. But we do have that stopping early check where if I ever do a single pass and nothing gets flipped, then it's already sorted. So worst case scenario, best case scenario is you give me a collection that's already sorted. I start doing bubble sort. I compare all adjacent pairs. If I flip nothing, I conclude it's sorted. I only ever have to do one pass. Best case scenario, it's linear time. That was very disruptive. My goodness.
Not expecting that.
The worst case scenario is if the things are in reverse order. You figure if I had like 9, this marker's not very good. One of these is good. If I had the numbers in reverse order, 9, 8, 7, 4, 1. Think of how many passes I must do. Well, after one pass, the 9 will be where it belongs. After the next pass, the 8 will. Then the 7, and then the 4, and then the 1 by default, with the 4 being in the right spot. So the worst case scenario is if it's in reverse order. If that's the case, I'm guaranteed to have to do like this n squared amount of work. So there is a best case scenario, there is a worst case scenario. Then the next sort we looked at was insertion sort. And the insertion sort idea was probably something you've used before, where what you do is you've got your unsorted pile and your sorted pile. How you differentiate this is up to you. Here, they're doing it all in a single array where you just have the sorted portion of the array and the unsorted portion of the array. But the idea is I pull something from the unsorted pile. I just pull something to take one thing out of its constant time. But then I need to find where it belongs in the sorted pile. So I have to scan that sorted pile to find where I can insert it such that it's where it belongs and the collection remains sorted. So like the 7, it's got to, well, that's a silly one. Look for the 2. You got to scan, 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 scan. There it goes. And if you do it like that, the insertion step is linear time. Because worst case scenario is, like the 1 in here is going to be the worst case scenario. It's got to go all the way to the end. It's got to look at everything in the sorted pile to find where it belongs. And I have to do this linear time search n times, 1 for each element in here. Now, we did talk last time, like, well, you know, the first time you do a scan, it's not linear time, it's constant time. You just add something to the sorted collection. But every time you add something to that sorted list, that sorted collection, it takes longer and longer time to scan. But we did a little bit of that analysis, and it's still n squared worst case scenario, right? Because, well, the first time I add something, it's actually easy, but the last time I add something, the worst case scenario is actually order n. So on average, when I go to insert some arbitrary thing into a sorted collection, on average, it's going to fall somewhere in the middle, you know. So we kind of used our intuition to be like, well, it's n squared. We also drew that literal square, right? We saw it was half the square because the first time, if this was n, 0, n. When I pull the first thing out, scanning, I only have to compare it to, well, nothing really. I just add it there. The next thing, I've got to do twice as much work, and then a little bit more work, and then a little bit more work, and then a little bit more work. Because as that sorted list grows, I have to do more and more work. But as we get down to the end, it's just, there's another one there. You can even see, like, geometrically, it's literally a square. I mean, it's half the square, but we don't really care about coefficients, whatever. So, there. But, you know, we also talked about how this one has a best and worst case scenario as well. But it kind of depends on how we scan the elements. In this particular one, the best case scenario, because you'll notice that when we take something from the unsorted section, we're scanning right to left, right? The reason we're scanning right to left is kind of arbitrary. I could have scanned left to right to find where it belongs, but I guess scanning right to left has a little bit of an advantage programmatically just because you can always just move things down. Whatever. That's more of an implementation thing and if it's an array or whatnot. But the reality is the direction in which I scan the things is entirely arbitrary, but it has an impact on what the best and worst case scenario is. With this particular example, the best case scenario would be if the elements are already sorted. Consider this, right? All right, 1. I want to add 1 to the sorted section. Oh, okay, great. Whatever, it's just there. This is now the sorted portion. Now I want to add the 4. All right, is 4 bigger than the... Oh, it is. Great. So I don't actually have to scan here. And then 7. Oh, 7 actually belongs here. I don't have to scan the sorted section at all. I just add it and then... Oh, similarly. Whenever we're just kind of like tacking on to the end of that sorted section, it's always a constant time thing. We never had to scan this whole unsorted thing, or pardon me, the whole sorted thing. So we get lucky. But if I scanned left to right to check for the sorted, it would be entirely different. Let's say I already have the 1 in the sorted portion. If I started looking here, I'd be like, okay, does 4 go on this side of the 1? No, it must go on this side. Then I would do it again for 7. Does 7 go in front of the 1? No. Does it go between them? No. Oh, it must go after. So if I'm scanning this way, suddenly that's actually now, if they're in order, worst case scenario. So the best case scenario would actually be if they're in reverse order. But it really does depend on how you implement it. But the idea that I want to emphasize is there could be a best and worst case scenario for these sorting algorithms based on the state of the data that you get. And what that is could depend on exactly how you've implemented the algorithm. Insertion sort says nothing about how you scan the sorted portion. This is insertion sort. You select something from an unsorted pile and you insert it into the sorted pile where it belongs. That's insertion sort. That's it. Now the last one we're going to look at is selection sort. And selection sort is very, 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 very similar to insertion sort. Remarkably similar. It's just kind of like the opposite. What you do is instead of taking something here arbitrarily and finding where it belongs over here, what you do is you find the thing in here that must go at the end of the sorted list. So the difference really comes to where I'm doing the scanning. I have my unsorted pile, my sorted pile. With insertion sort, I take something from the unsorted pile and I scan the sorted pile to find where it belongs. Selection sort, I scan the unsorted pile to find the smallest element remaining in the unsorted pile. I take it out and I tack it on the end of the sorted pile. If it's the first thing, whatever, it's the only thing there. So that's what's happening here. Scan for the smallest remaining thing, 2. Scan for the smallest remaining thing, 3. Okay, scan for the smallest remaining thing, it's the 4. And you just tack it on to the end of the sorted portion. That's how it works. The fact that it swapped where the 0 and the 8 was, kind of arbitrary. You could have shuffled everything down, I guess, but it's easier that way programmatically. But hopefully you can get a sense of how this is a remarkably similar algorithm to insertion sort. It's just where we're doing the scanning, right? But they're very similar ideas. Raise your hand if you think you've ever used this sorting strategy ever in your life. Put up your hand. I know you have. Everyone has. It's simple, it's intuitive, and it's going to work. So let's take a moment and think about the worst case scenario. If I'm scanning a collection, an unsorted collection, maybe it's sorted, maybe it's not. I have no guarantee on if it's sorted or not. If I'm scanning it, what's the computational complexity of finding the smallest element? That's too precise. Complexity, be lazier. N. That's that. I have to scan that collection for the smallest element. As far as I know, the smallest element, there could be 100 things in that collection. I could be looking at the 99th one, and it's a 0. Can I guarantee that that's the smallest thing? No. I have to look at all 100, right? Okay, so to scan a collection, it's going to be linear time. And how many times am I going to have to scan that linear collection? Well, once for each of the n elements, right? So I have to do linear work n times n squared. Great. But what's the best and worst case scenario? Because remember, with bubble sort and insertion sort, the state of the data had an impact on the running time. But what's interesting about selection sort, with bubble sort, we could stop early as soon as we did a pass where nothing was flipped. With insertion sort, when I'm doing that scan for where it belongs, I can stop the scan early as soon as I find where it belongs. Right? Remember when I kept tacking on to the end? Oh, does the 8 go here? Yeah, no need to scan. I don't need to keep looking. Each addition, each insertion ended up in the state where it was already sorted and I was scanning this way. Each addition actually ended up being constant time in the best case scenario. There is no way I can stop early on a scan for the smallest element in the collection, though. I can't, because until I've looked at everything, one, I'm going to need to scan this thing n times, because I have n elements. You can say n minus 1 because the last one's a freebie, fine. But n, because we're lazy computer scientists. But the time it takes to do that scan, that linear time bit, where that linear time portion of the scan for insertion I could end early. For bubble sort I could end early. The ending early had to do with the number of scans I was doing. Where the insertion ending early happened on the scan itself. With selection, there's no ending early option. No matter what, I have to do a linear amount of work to find the smallest thing. Because like I said, I could have a bajillion elements. And if I've looked at all a bajillion minus 1 and have a 0, and I haven't looked at that bajillionth, I have no guarantee that I actually have the smallest yet. Until I've looked at everything, no matter what, I don't know if I have the smallest thing. And because there's no stopping early here, there is no best and worst case scenario. No matter what, this is always going to be quadratic. No matter what, it's always n squared. So with bubble sort, best case scenario given the state of the data, it could be linear. Insertion, depending on the state of the data, could be linear. Selection, it doesn't matter. Always going to be quadratic. Always going to be n squared. And that kind of sucks. The good news is, these three algorithms suck no matter what. Right? And you got to figure, well, there is a best case scenario. But on average, the other ones are going to be like half n squared, but we don't care about half, so they're all n squared no matter what. But in practice, it'd be interesting to actually run these and compare the time it takes to sort these things on average, to see if there is a difference. Any questions about this selection sort? Now, if you're ever having a hard time remembering which one's which, for me, I never had a hard time remembering bubble. Bubble was different enough, right, that it was just, whatever, you do that, you're always comparing adjacents and it bubbles up. Selection and insertion, given their similarity, I always kind of had a bit of a hard time remembering which one which. But I don't know, what I did to remember was, with insertion, I inserted into the sorted list. With selection, I selected from the unsorted list. Like the intelligence, I realized with insertion, well, you're selecting from the unsorted list too, but that was arbitrary. I just randomly grabbed one. Selection, I did the scan on the unsorted to select the smallest. Insertion, I'm scanning the sorted portion to find where I need to insert that arbitrary thing. That's how I remembered it. Okay. Any questions about bubble, BOGO, insertion, or selection? Now, like I said, those algorithms all kind of suck. And one of the big reasons they all kind of sucked was because, you know, I had a collection of n things. And in order to sort them, I needed to compare those n things to everything else. I needed to compare each thing to everything else, and there's n of them. So I need to compare each of the n things to n other things, n minus one other things, I guess, because you're not going to compare it to itself. But again, lazy computer scientist, n things to n other things, yeah, that's n squared, right? It's like n times n, if you really want to be lazy. But I wonder if there's a way we can sort things by not doing that. Merge sort. Just have a look at the animation and we'll talk about it. There you go. There's merge sort. Did that make sense to everybody? I'm seeing like, oh yeah, totally. There are two important concepts we need to understand. Let's call it 2.5. The first 1.5 is an empty list and a list with one thing in it are, by definition, sorted. I'm one person standing in the front of this room right now. And I want to sort everybody in the front of this room right now by height. Is this collection sorted? Well, nothing's out of order, that's for sure. How about everyone standing along that wall? Are they in order by height?
Sure.
Yeah, I mean, there's nothing out of order. They're sorted. There's no ifs, ands, or buts. If you have, it's easier to kind of rationalize about a list or a collection size 1. If you have one thing, there's no way that one thing can be out of order. It's just itself. Right? The next thing is it's actually remarkably simple to merge two sorted lists. Here's the algorithm for merging sorted lists. The trick to this working is the lists have to be sorted. What you do is you compare the two things at the front of the two sorted lists. The lists don't even need to be the same size. So right now I'm comparing the 2 and the 1. What's smaller?
1.
Thank you. Boom. We add that to the sorted bit. Now we compare the 2 and the 3. What's smaller? All right, great. You take it out and add that to the sorted bit. Now compare the 5 and the 3. 3. The 5 and the 4. The 5 and the 6. The 8 and the 6. The 7 and the 8. Or the 8 and the 7, whatever. And well, now, I mean, there's nothing left in the other one. And I know that the contents of this list were already sorted, so I can just take the remaining and just tack it on to the end. And if I do this, I end up with another sorted list. But that sorted list is bigger, right? Because I merged the two. So given 2 sorted lists, I can merge them really easily. The algorithm is simple. Compare the 2 smallest things, the beginning. Remove the smaller one and add it to the sorted chunk. Now let's think about the computational complexity of that. Right now, let's assume, for simplicity, let's assume the lists are the same size or roughly the same size. They're not wildly different sizes at least. So maybe something kind of like this. Let's say they're both length n. How many, worst case scenario, how many comparisons am I going to have to do?
Log n.
No. You might be thinking too big right now. This is just merging the lists. I have to compare the 2 and the 1, right?
Oh, it's just linear.
Yeah, it's going to be linear, right? Obviously, if I have 2 lists of roughly size n, the new sorted list is obviously going to be like 2 times n then, roughly, right? Because if I have a list of 10 things and another list of 10 things and I merge them, I have a list of 20 things now, right? So you could say like, okay, given that, you're probably thinking it's going to be like 2 times n units of work, but of course that's just linear, we don't care about coefficients. So the amount of work it takes to merge 2 sorted lists is actually linear time. It's great. So here's the idea. Let's start by breaking all the lists down. We start with our collection, you cut it in half. Cut those in half, cut those in half, cut those in half until you end up with n lists of size 1. Okay? So now I have n lists that are all sorted. Right? I'm not being silly. If I do that, I have n, for the sake of simple math, let's assume n is a nice power of 2. So we can divide it by 2 repeatedly and end up with things of size 1. I might have a nice visualization down here. Do I? Yes. Right? So assuming it's a nice power of 2, I can repeatedly split this until I end up with, instead of 1 list of size n, I have n lists of size 1. And the good news is each of those lists of size 1 is sorted. The other good piece of news is, I know you know a nice algorithm to merge 2 sorted lists in linear time. Right? So all I have to do is merge those. I can take 2 lists of size 1 and merge them. And do that again, and do that again, do that again. Until what I'm left with is n over 2 lists of size 2. Right? Then I can merge all those until I have n over 4 lists of size 4. And I can keep doing that until I have 2 lists of size n over 2 that are sorted. I merge them and I end up with a sorted list of size n. If I have, I have n elements to start with. And I'm breaking it down into n lists of size 1. So right now, what I want you to do is think of this bottom row here, this bottom level of this tree. Okay? Obviously, to merge 2 lists of size 1, That's like 2 units of work, one for each of the size 1 thing. But of course, I don't, on that bottom row, I don't just have 2 lists of size 1. How many lists of size 1 do I have? N. So, if I have to merge all n of these things, how much work is being done to do all of those merged on that whole row? N. I know it maybe felt like N. Yeah, absolutely. Your intuition is right. To merge these two, it's like 2 units of work. To merge these two, it's another 2 units of work. To merge the next two, it's another 2 units of work. But if I have n of those things that need to be merged, merging them all, doing all the merges necessary to end up with n over 2 lists of size 2, I have to do like n units of work on that level. Now let me ask you, how much work has to happen at that next level? If I have n over 2 lists of size 2, I take 2 lists of size 2. How much work is it to merge those? Well, it's like 4 units of work, 1 for each of the things, 2 and 2. But I don't have only 2 lists of size 2. I have n over 2 lists of size 2. So how much work is going to get done on that next level up? How much? We're being really loosey-goosey with our precision here. What were you going to say?
2n?
2n? Not quite. The trouble is, because we're being loose with our terminology and the precision on it, you both could be right. One said n over 2, someone said 2n. Let me put it like this. If I had 2 lists of size 2, that's 4 units of work, right? I'm just saying like 2 times 2 equals 4, right? If I have, like I took 2 lists of size 2, but I actually have n over 2 lists of size 2. N units of work, yeah. Right? Because, it's n. And then similarly, if I had 2 things of size 4, that would be like 8 units of work. That would be the next one up. But of course, I don't only have 2 lists of size 4. I have n over 4 lists of size 4. Well, that's like n units of work. Each level in that tree, I have to do like n units of work. So for each level, to do the merging, I have to do n units of work. We can do this all the way up. Imagine I have 2 lists of size n over 2. Right? If I have 2 lists of size n over 2, before this was the number of lists, this was the size of the list. Now we're at the other end. This is the number of lists I have. This is the size of each list. How much work is there on that second last thing to do the merge to the final list of size n? It might just be n. Yeah. I think you're right. Why? Because that's arithmetic. So there we go. Now obviously we're being loosey-goosey. We're just using our intuition here. But for each level in that tree, there's n units of work. Now the question I have for you, and you all better know the answer to this, and if you don't, you should all feel really bad about yourselves. What is the height of this tree? Log 2 of n, absolutely. Everyone knew that, right? Why? Because we had n things, and we divided by 2, divided by 2, divided by 2, divided by 2, until we run out in log base 2. So, if I have to do n units of work for each level in that tree, and there are log base 2 levels in that tree, how much work am I doing in total?
N log 2 of
n log base 2 of n. Absolutely. This is order n log 2 of n. And we can wrap that in more parentheses if we'd like. Amazing. In case you forgot, n log n, again, in computer science, whenever you hear log, assume base 2 until told otherwise. Which is nice because dividing by 2 is nice and fun. N log n is a hell of a lot better than n squared. This sorting algorithm obliterates the 3 we've done before. But let me ask you something. And there's always going to be an asshole in the room that's going to lie. But let me ask you something. Clearly we can see this sorting strategy way better than the other 3. Yet, how many of you have sorted a collection of things with this algorithm, more or less? That's what I thought. We don't have any liars this year. Yeah, bullshit you did. I know. Every year there's usually one person that's like, oh, I have. It's like, yeah, you have. Sure you have.
You should make that 2.
Pardon? You should
Make that 2.
two jerks? See, the reason you know no one's done it is because the amount of, like, room you need. Like, if I gave you a collection of books to sort alphabetically or something, maybe I give you like 100 books. If I've got to sort those 100 books, no, let's say I've got, let's say, what's 2 to the 10? 10, 24, perfect. If you had, 10,024 books to sort alphabetically, right? Just to get a sense of how much work this would be, the n squared algorithms, if you were to use insertion sort or selection sort or bubble sort, you know, you're looking at 1,048,576 comparisons, roughly, to sort those things. Maybe we could divide that by 2 because really we know, right, on average. That's still a big number, right? But, let's just go to 10. This is only going to be, oh, it didn't work.
No solution to this.
Perfect. It's just this times 10. The reason I know it's 10 is because 2 to the 10 is 1024. It's basically just this times 10. So either we got 1,000,000 units of work or 10,000 units of work. And as n gets bigger and bigger and bigger, the discrepancy between the amount of work is going to grow catastrophically large. So obviously, if I gave you an option to do something that's going to take like 1,000,000 units of work or 10,000 units of work, you're probably going to want to do the thing that takes 10,000 units of work, right? Yeah.
Is the discrepancy just going to be n over log base 2n? Because you do n squared over n log 2n.
You mean like the difference?
Yeah.
Well, yeah, we can, yeah, you would just do the calculations.
The ratio of the big number to that number is just going to be n over log 2n.
Well, it'll be n squared minus n log base 2 of n.
Right, that would be the difference.
Yeah.
Right.
So obviously this is going to be better, but you got to figure, the problem with this is it takes up like kind of a lot of space, right? Because I got to get those 10,000 books, and then I've got to break them down into smaller groups and 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 smaller groups. Or if I just had 2 piles of sorted and unsorted books, that's, I just need these 2 piles. There would be big piles, there's 1,000 books. But if I need to start breaking things down to look like this tree, I don't have enough room. I'm gonna need a lecture hall, a gym to do this. And so when you have some jerk that's like, yeah, I totally used this sort before. No, you didn't. Anyways, point being. That's the computational complexity. So here's kind of showing you how to do it. Now, this algorithm is actually hilariously simple to implement recursively. So define merge sort. If the list is of size 0 or size 1, return the sorted list of size 0 or 1. Right? So here's the recursive algorithm for merge sort. If the size of that list is 0 or 1, return that list. It's a sorted list. If it's not, here's what you're going to do. Split that list into the first half and the second half. Split it in half. Sort the first recursively. Sort the second recursively. Now, once that's done, I have two sorted lists. Now I just do that merge algorithm. That could be iteratively defined. I'll just call a function to do that. Now I have the bigger one, return it. I know it sounds like I'm cheating, but that's kind of how recursion sounds a lot of the time. If I'm size 0 or 1, return it, I'm sorted. Otherwise, split it in half, sort that side, get them back, merge them, and return the merged sorted list. And then you go, well, hold on, you just said sort that side and sort that side. How do you do it? The exact same algorithm. You just call it again on the smaller lists. Great. Cool. Now, quicksort. Quicksort is another one that could be really good. But unlike merge sort, quicksort could suck. The idea behind quicksort, there's 2.5 ideas behind quicksort. The first 1.5 is a list of or a collection of size 1 or 0 is sorted. We've already agreed on this with merge sort. Okay? Now, here's the second idea. Let's say I'm some arbitrary number x. And I have a sorted list of numbers that are less than x over here. And a sorted list of numbers that are greater than x over here. And I take this list, and I tack it onto me here, and I take this list and tack it onto me here. I now have a bigger list that's sorted. Because if these are all sorted, and they're guaranteed to be sorted, this number comes after that number, all these numbers, still sorted. And then another list of sorted things over here that's guaranteed to be sorted, and they're all bigger than x, maybe equal to, whatever. And you tack it onto the end, you just have a bigger sorted list. So here's what we do. Here's quicksort. Here's the idea. You start with your collection. You pick some point in that collection, some arbitrary number in there, you're going to call the pivot. You pick it. Then you go through all of the numbers in that collection, and all the numbers smaller than x, you put over here. All the numbers greater than x, you put over here. You sort those. You get them back, you stick them together, and you return it. But again, you ask, sounds like you're skipping a step. You just magically put all the small numbers over here. Okay, fine. That can be done in linear time, right? Just scan it, smaller, smaller, bigger, smaller, smaller, bigger, bigger, right? And then I say, just go sort it. How? That same algorithm. In this list of smaller ones, you pick a pivot. All the ones smaller, you put over here. Bigger, you put over here. Repeat that process. Eventually, you'll get down to lists of size 0 or 1. They're sorted. You kind of tack them back together. You end up having a sorted list. This is fantastic. So quicksort, the idea, it's recursively, we can describe it really easily. You pick a pivot, smaller elements, bigger elements, you sort them, you get them back, and you tack them together. That's it. And if at any point you're saying, but what about, I haven't skipped any steps, it's a recursive algorithm. If the size of the list is 0 or 1, you're done. It's a sorted list. You return it. to whoever asked you. That's the algorithm. But what's the complexity? Okay, quicksort algorithm. If the list is size 0 or 1, return the sorted list. Otherwise, select a pivot. All elements less than go into a list. All elements greater than go into the second list. Sort the first list, sort the second list, concatenate the list, return the list. The analysis is going to be the same, except there is a big asterisk on this algorithm. And we'll pick up here tomorrow. Don't spoil it. Or spoil it. Maybe, I don't know.